Good morning all of you. Myself Engineer Jyoti Prakash Beura from Electronics and Telecommunication Department of BOS Cuttack. Today I will teach you about operational amplifier, which is the most important subject of analog electronics and linear IC. So let's start with the definition of op-amp. Before that, we know what is an amplifier. We know an amplifier is an electronic device which will increase the strength of a weak signal, or we can say the amplitude of a weak signal. Suppose this is the amplifier and this is the input of amplifier. If we give a signal like this, then the output will become like this. So it indicates that the amplitude will increase here. So why it is called operational? So let's see the definition first. An op-amp is a high gain versatile device which will amplify AC as well as DC signal and specially designed to perform some mathematical operation like addition, subtraction, integration, differentiation, etc. So the gain of the operational amplifier is very high and it's a versatile device. Versatile means a single thing can do many operations. That means operational amplifier will amplify the signal as well as do some mathematical operation. That's why it is called a versatile device. Let's see the symbol of op-amp. As you see, two input voltages are here. One is V1 and another one is V2. V1 is given to the positive end and V2 given to the negative end. And here is the output voltage. So the positive voltage is known as the non-inverting input and the negative end is known as your inverting input. So it is mandatory to give two input of equal amplitude and opposite phase to the amplifier, and the operational amplifier will take the difference between the two voltages, which is also known as VID. VID stands for input differential voltage, and here we will get the output. The gain of the amplifier is represented as A, capital A. So we can write the formula for gain. A is equals to V output or output voltage divided by the input voltage. Here the input voltage is the difference between the two voltages. So in the place of V in, we can write the difference between the two voltage, V1 minus V2, or we can say output voltage divided by your VID. Similarly, by doing cross multiplication, we can write output voltage is equals to gain multiplied with VID. Now I will show you the basic block diagram of a typical op-amp. So the first stage is the input stage. The second one is the intermediate stage. The third one is the level shifting stage. And the last one is the output stage. So in the input stage, we use dual input and balanced output differential amplifier. In the intermediate stage, same dual input and balanced output differential amplifier. In the level shifting stage, we use emitter follower amplifier. And in the last stage, that means in the output stage, we use complementary symmetry push-pull amplifier. The whole total is the block diagram of typical op-amp. Next, we will discuss about the characteristics of an ideal op-amp. So the first one is the input resistance of an ideal op-amp is infinite. The output resistance is 0. Gain is infinite. Bandwidth is also infinite. CMRR is infinite, and the last one, slew rate, is also infinite. So two new terms comes here. One is CMRR and another one is slew rate. I think you have doubt in your mind what was that. So now I will explain you about the CMRR and slew rate. So CMRR stands for common mode rejection ratio. Actually, the input voltage to a differential amplifier is of two types. One is differential mode voltage and another one is common mode voltage. So what is differential mode voltage? If we provide or if we supply two voltage of equal amplitude and opposite in phase, then we call it differential mode voltage. And if the two voltages are equal in amplitude and equal in phase, then it is called common mode voltage. But remember one thing, op-amp rejects the common mode voltage and always prefer the differential mode voltage. Because if we give here a plus 15 volt and minus 15 volt of supply, then the difference between the two, V1 minus V2, is equals to 15 minus of minus 15, that is your 30 volt, which is input to the op-amp. But in case of common mode voltage, if we provide here 15 volt and here provide plus 15 volt, then 15 minus 15 is equals to 0 volt. Here no input is given to the op-amp. So op-amp always rejects the common mode voltage and prefer the differential mode voltage. And what is CMRR? So in case of differential mode voltage, if we found the gain, differential mode gain, then it will become VODM divided by VIDM. Differential mode output voltage divided by differential mode input voltage. Likewise, in case of common mode, the gain will be, common mode gain is equals to VOCM divided by VICM. Common mode output voltage divided by common mode input voltage. So finally we can write the formula for CRR is equals to ADM divided by ACM. So or you can say CMRR is defined as the ratio of differential mode gain to the common mode gain. So what is slew rate? It is defined as the rate of change, the maximum rate of change of output voltage with respect to time. Mathematically you can write d by dt of output voltage. So unit is volt per microsecond. So this is your slew rate. So last thing is the pin diagram of nowadays op-amps are available in the IC form. So we are using commonly IC 741 for the purpose of mathematical operations like addition, subtraction, integration and differentiation, and for the most of the practicals conducted in the laboratory. So let's see the pin configuration of IC 741. So it's a 8-pin package. So here is a spot, dark spot here, which is called as a notch. It was here to show you what you can count the pin from the top of the right side of the IC. So here the pin number 1 is the pin number 2, this is the pin number 3, is the pin number 4. Then comes to the bottom of the right side, pin number 5, 6, 7 and 8. So pin number 1 is your offset null. Pin number 2 is your negative input, or you can say this is inverting input. Pin number 3 is your positive input, that is non-inverting input. Pin number 4 is your negative supply voltage. Pin number 5 is again offset null. Pin number 6 is your output voltage. Pin number 7 is positive supply voltage, and pin number 8 NC, that means no connection. So you will give the negative supply to the pin number 2. Positive voltage to the pin number 3. You get the output from pin number 6 and provide positive DC voltage at the pin number 7 and negative DC supply at pin number 4. To make it a complete 8 package, a dummy pin is there which have no functions within this operation. This is called no connection pin. So this is for the purpose to make it a complete package.